we're going to be having a really exciting panel on future embedded systems. A bit of bookkeeping. You could use the Zoom Q&A for asking questions, but they don't work really well. So I would recommend everyone to post their questions on the Slack channel. And the Slack channel is SIGCOMM 2020 panel embedded. So we have a very interesting set of people on this panel, a very diverse set of people on this panel to talk about embedded systems and the future of embedded systems. We have Luca from Italy, who is an expert in embedded systems and more recently has been working on nano satellites and CubeSats. We have Tanzeen Chowdhury, who is a professor at Cornell Tech. She's one of the experts in mobile health and embedded systems and mobile systems and has had significant impact in that domain. And finally, everyone, I'm Shyam Golakota from University of Washington, and I have worked on things like backscatter communication. And more recently, I've been working on bio-inspired and bio-integrative embedded systems. So just to give some context for what this panel is about, it's about embedded systems. And if you look at the traditional definition of embedded systems, it's about embedding, computing, sensing, and communication into everyday objects. And this includes the most conventional things which we are all familiar with, such as the Nest temperature sensor, the Ring cameras, or a variety of different sensors we all use for our security systems. This is what's been the traditional Internet of Things or embedded systems, which has mostly been about having communication and some sensor like a temperature sensor, which is providing the information and sending it to the cloud. But the whole hypothesis of this specific panel is that the next gen embedded systems are going to go beyond just sensing. In particular, we are going to start talking about things which can actually move, embedded systems which can actually move. So here is one of the systems which we built where we can have the system which is as small as a RoboFly, which can lift off and actually move, and it has computing, it has communication, and it has sensing embedded into it. Or we are also increasingly seeing wireless systems that are embedded and integrated with living insects, such as bees, so that they can collect data about what's happening in a farm. And more recently, we're also seeing things where we can create hybrid insect robots, which are all, again, embedded systems. So in this video, what you're going to see is a robotic arm, which can move, and you can collect a panoramic view of what's actually happening, a panoramic video of what's actually happening, and it's streaming that to a mobile phone. So it's not just limited to micro robots, the future of embedded systems. You're also seeing increasingly work, which Luca is going to talk about, where wireless systems are being embedded into nano satellites, and things which Tanzeen is going to talk about, which is how we can actually embed systems to enable healthcare. So this is basically the cover of Nature Medicine from June of this year, where they talk about wireless biosensors, which can be used for neonatal ICUs. So we have an exciting variety of different topics which are going to be covered for embedded systems. And the way we're going to structure this panel is that we're going to have Luca and Tanzeen talk about 3 to 5 minutes about the kind of work they're doing so that they can provide better context for SIGCOMM. And then we're going to open the floor for questions. With that, Luca, the floor is yours.
All right, thank you. Shyam, are you gonna share the screen yourself with my slides as we agreed?
Oh, it's already sharing. The screen is already sharing.
But I still see your last slide. I don't know if it's only me or what.
I think it's showing me the Beyond the Clouds embedded software for nano satellites.
Okay. Well, whatever, let's go ahead. I still see yours. Anyways, so first of all, I wanted to thank you, Shyam, for the invitation. It's a pleasure to be here. I'll be real quick, as I just want to throw out a few things and then open the floor for discussions. So what I'm gonna talk about is something that really excites me, It's a very interdisciplinary area with lots of uncharted territory, and it's not a pun. So please, next. So let me start off by telling you what we are exactly going to talk about. Next. So a nanosatellite is nothing but a satellite with a certain size and weight restrictions. For example, we talk about nano satellites where we are considering devices that weigh less than 10 kilos. And among them, among nanosatellites, there's a sort of standard that is emerging with what we call CubeSats, where each device is guess what, is a cube of exactly 10 centimeters in size, and it must weigh between 1 and 1.3 kilos roughly. And these specific features are there for a reason, because they greatly facilitate loading these devices on the launch rockets that are the vehicles that put the devices into space, and it makes their deployment a lot easier when you are reaching the target orbit and it's time for the launch rocket to release the device. Next. So a typical, you may be wondering what is the payload for these devices. So typically a CubeSat is carrying a camera for remote sensing, a set of small solar panels, and some RF subsystem for communication. Because of the size and the weight constraints, now CubeSat has very strict limitations in terms of energy consumption, processing power, and communication capabilities. Which is where actually we embedded system people come in, and then the fun begins for people like us. So next, I wanted to give you a couple of examples now of the kind of work we have been doing in this area. Next. So one problem we have been working on is how to perform energy efficient localization in space. So CubeSats have a GPS, pretty much like your smartphone, that is used for both application level positioning and for the general navigation once the target orbit is reached. Typically, you would use duty cycling for achieving better energy efficiency for the GPS receiver. The problem is, unless the local time and information about the visible GPS constellations are known a priori, what you normally need to do is to search for all visible GPS satellites, estimate the Doppler shifts, and correlate the so-called pseudo-random noise codes, the PRN codes, that are unique for each of the satellites. Now, the scenario is a little bit different compared to when you're on Earth, because a CubeSat may actually travel at 8 kilometers per second at 500 kilometers from the Earth. And the GPS satellites themselves, they move around at about 4 kilometers per second. So the receiver and the transmitter move relatively to each other really fast. The CubeSats do not have a sophisticated navigation system, so what you end up with in most of the cases is that CubeSat keeps spinning on itself. It keeps tumbling around the orbit. That makes things a lot worse for estimating the Doppler shift, which becomes extremely large, and it will take you a lot of time before you get the first fix. Now, this may actually take up to 30 plus minutes for you. And duty cycling makes no sense in that scenario, because if you want to keep the GPS on for half an hour just to get a first fix, then there's no reason to shut it off at all. So what we have developed is a hardware software system called Hummingbird, which we are going to present at Movicom in a couple of months, where we have a motion estimation technique based on data that you load on a microcontroller before launch, that allows us to reduce the time to get the first fix from like half an hour up to tens of seconds. And that is a great improvement in terms of energy efficiency when it comes to the figure that goes into the GPS receiver. Next. So another problem we've been working on is how to understand when and what goes wrong on a CubeSat. The opportunities to communicate down to the Earth are very slim because the bandwidth is extremely constrained, and the radio operation is also energy consuming. So forget about anything like a periodic ping down to the Earth saying, hey, I'm here, I'm alive. But what's most challenging is that whatever monitoring system you want to deploy, it must be as decoupled as possible from the CubeSat, because you don't want to affect the operation of the CubeSat because of the monitoring system. And in addition to that, you want to have an easy way to convince the people who are going to put your device on a launch rocket nothing is going to go wrong just because of your monitoring system. We've been working on this very challenging problem for a lot, and now we have a solution that we call the Smart CubeSat Tracker that is completely detached from the CubeSat, meaning that there's not even an electrical connection to the CubeSat. It's all about passive probing, understanding from like the outside of the CubeSat how the CubeSat is doing, and through a separate RF communication system, we can send down the very minimum amount of information that allows us to understand whether everything is fine or not up there. Next. So I'm really only scratching the surface here. There's a lot more into this area, but to be researched and to be discovered in a way. And as I mentioned at the beginning, what I like the most here is that you get to talk to people with a very different background than embedded system. You need to talk to aerospace engineers. You need to talk to the people in charge of the launch station. And often it's really two different languages that need to come to a common agreement. Next, if you want to know more about what we're doing in this area, you are welcome to check out the website of our lab at www.nestlab.it. Yeah, and that's it from my side. Next, I'll be happy to answer questions.
All right, thank you so much, Luca. Next, we're going to have Tanzim talk about mobile health and embedded systems.
Okay, thanks, Shyam. I'm going to talk about a specific aspect of mobile health where I think there is a lot of kind of opportunities of new innovation, particularly in terms of going beyond embedded sensing to embedded actuation, and what particularly as we kind of move into the new world of, I would say, health, where a lot of measurement and actuation is happening in person's own environment, so in an immersive context, and what from our perspective, we saw some of the gaps, and I'll give one simple example, but I just want to kind of position that this area where I think there's a lot more opportunities for doing kind of innovative work. So going to the next slide. There has been a lot of technical advances in health and health sensing, particularly, and there's been parallel advances in the clinical side. But I think sometimes these happen in parallel with with not as much crosstalk and iterative design that needs to happen. And going to the next slide, one of the things that we have been kind of actively trying to do for many years is really make that an iterative process to understand where the sensing and actuation can have impact, and how do we design a system that could actually be adopted and used widely. So one thing that I wanted to highlight is, I would say we've done made huge progresses in the context of measurement, right? So there is a lot of work in sensing that now can capture a lot of aspects of health, but where I would say there's still a big gap is how do you intervene on someone's health? So if we go to the next slide, I would say that there is a huge set. If you go look for even apps, there's huge slew of apps out there that is claiming to do intervention, but I would say that the sensing and intervention still are not very intimately coupled beyond some what I call simple bookkeeping, right? That you have an achieved your goal. These are my suggestions that from the app based on mining your data. And kind of going next is that what we want to see is how do we close that kind of gap and have a continuous loop and not just something that is looking at summaries and trends, but it is doing continuous measurement and intervention. So if we go to the next slide, I would say we want to kind of mimic the trajectory of how we went from sensing, right? If we think about health sensing in the natural environment, right, before sensing, right, people would log and journal, and that is still used in the health context of when the doctor asks you to log or journal certain behavior. Going to the next kind of version, the phone kind of revolutionized that, but first step by just making it easy for someone to log, and then the next step was where the sensing came, is made it invisible, right? You did not have to put a lot of effort into recording every aspect of your behavior, and that was done with the phone is one example, but the embedded sensing enabled us to really make that process very easy and seamless for the user. So now, can we do that same thing for intervention, right? I would say that health intervention technologies now, as we have it, particularly in a person's natural environment, is expecting too much for us, from us. So going to the next slide, one of the things that we have been kind of thinking about, can we design intervention that doesn't always require us to be consciously aware and acting on what is being measured. So if you think about sensing, right, the sensing is happening passively, it's not putting burden on us, but in all of the intervention that is designed, it requires us to process that information and make a decision and act on that. So are there opportunities to doing that invisibly similar to sensing? And I'll give one example, and I think there are a broader set of things that we can be working on, is we wanted to look at impacting physiological signals. So for example, we can measure heart rate, breathing rate, other physiological sensing. Can we influence that through kind of embedded actuation? So there is a whole notion in psychology which calls the interoceptive awareness, is how people are aware of their internal bodily changes, not always consciously, but they kind of some are more aware than others, and there has been some literature that shows that people who are more aware of their physiological changes can be more prone to anxiety and depression, because they, as soon as their heart starts pounding, they become it's a kind of a feedback loop where they get more anxious. So one example we wanted to do is, if we are continuously, next slide, measured, can we try to actually influence that signal in real time to impact someone's anxiety? And ultimately, if we can impact instantaneous anxiety level, then it might also have secondary impact of improving like alertness, concentration, performance. So next slide. What we did is, where we were constantly looking at, it's a very simple example of measuring someone's heart rate during stressful tasks. So here, someone's heart's beating at 110 beats per minute. You can have some kind of actuation, and in this case, tactile feedback that is happening that mimics that heart rate. But what you can also do is, going to the next slide, is alter that signal. So let's say if you slow it down and give feedback at slower than what your actual heart rate is, does that actually have a calming effect on you? So what we actually saw, going to the next slide, we've done this experiment in several contexts with hundreds of users, is you can actually impact person's anxiety level, self-reported measures of anxiety, and you can go both ways. You can actually increase anxiety or also decrease by giving that feedback. Going to the next slide, not only can you look at the self-perception of it, actual physiological change happens. So by giving that continuous adaptive feedback, you can actually change a person's kind of heart rate. And the impact of that, we have done that in the context of a math test. If you go to the next slide, that you can actually change performance. So we saw that you can improve a person's performance in the test by doing this continuous kind of measurement and intervention. So I want to kind of leave that. We are exploring various ways you can think about. We could constantly measure sleep. Can you measure do better sleep intervention this way? There are aspects of it that can be used in rehabilitation, where you're constantly measuring and trying to actuate to lead to better outcome. There is actually things that are used in gait and rehabilitation using kind of acoustic rhythmic effect, and I think there is opportunities of doing sensing and intervention there as well. So I want to kind of put out the call that as we develop more and more richer sensing, thinking about ways where, similar to kind of Sham started in the beginning, talking about kind of bio-inspired sensing, and also beyond just sensing movement. I think there is a lot of opportunities of integrating sensing and actuation in a closed loop system that actually makes health intervention in the wild really acceptable and scalable without putting a lot of burden on the user. I'm going to stop there, and we can kind of move into session.
All right. So we're going to open it up for questions. Please post your questions on the Slack channel. I'm going to stop the sharing of the thing. I'm going to start with the first question for actually Tanzim. I really found this concept of closing the loop to some extent, which basically you're having a sensor, it's just not sensing the data and just giving you information, but it's also kind of actuating and kind of changing the loop for you, which is very fascinating. I think that's the next future of mobile health. I guess the question I have for you is, because we're in SIGCOMM, can you articulate a little bit more of the systems level challenges, mobile systems level challenges one would face when we have to address? What are the challenges in making this happen?
Yeah, I think one of the kind of a few things, like the example I gave is simple, where we are capturing the heart rate information which you can get with instantaneously, and can do an actuation that really without any lag, right? So that communication kind of aspect of having no delay is really important. We try to do that in the context of voice. Again, you can do measurement, but people are very perceptive to the notion of delay if they're listening to their voice. So one example we did is where they would get a feedback in their ears where the voice was altered. So there, any little kind of change there will completely screw up the conversation. The other thing is that becomes more kind of complicated of how do you act on multiple signals, right? And accumulate multiple signals, and what modality do you actuate on? The other thing is to kind of keep track of one of the things is the adaptive aspect of it. So for example, one of the things where our signal sort of backfired was with the gait example that we did, where we were trying to actually get someone to walk faster. Oops. Sorry, Luca, are you saying something? Oh, no. So the gait example, it actually had a negative impact on heart rate. So some people, we actually ended up getting people to change their gait, but also impact their heart rate. So how do you kind of keep track of that multimodality of changes and adapt that actuation in a more intelligent way? This was just one signal that we are measuring and actuating. I think that multimodal aspect of it, and how do you adapt dynamically and also do it with without the conscious perception that you are doing it, that interferes with their actual task, is some of the things that we've been kind of thinking about.
So I'm going to actually focus on mobile health and then move to CubeSat so that we have continuity. I'm going to ask Anja's questions, which is, can you comment on the ethics of reporting incorrect or manipulated data to a user of a mobile health application. I think and more broadly, the other question is also about privacy. Once you're collecting more of this information and you're actually starting to affect the human behavior, what are your implications of ethics and privacy?
Yeah, so we did two versions of this experiment. One where we didn't tell the user, and the other time where we told the user that we might randomly actuate, give them feedback that is not accurate. We're going to alter that feedback. And we saw the similar effect. So the one is that will the effect last if the person knows that the effect is happening or alteration is happening? So the good news is that we can still have this, the effect persist. The second is whether it's ethical or not. I think there we were having users authentication authorization is very important, right? We in the context of kind of the testing, that you can say that this might help you, and it's your choice, just like sensing permission, right? Right now pretty much it's default that you would get the permission for sensing, and if the user is but at the same time there is a risk, right? So we need to think about, and I think that's another thing about, we have not at all looked into kind of the security aspect, right? Can someone tamper with that signal and send a false signal that, as you saw, that maybe we're trying to calm something down, and someone who is in a competitive exam context is trying to hack into the signal and making their classmates do worse, right? So I think there are aspects there that has to be handled, which we haven't done at all. But I think the biggest thing in the context of sensing is, I think similar to sensing, I think the users should understand what's happening, and the users need to kind of give permission and have control over the actuation.
Perfect. So, Luca, we want to shift a little bit to CubeSats, and one of the questions Romain had was, what is the bigger vision of these CubeSats? What kind of a sensing are they? What is applications? And are you talking about having cameras up there? What kind of a sensors? So if you can talk a little bit about that, that will be great.
So right now, I think the primary direction is to deploy there some sort of camera through which you can do some form of remote monitoring. For example, there's a lot of effort into developing RF cameras by which you can monitoring the movement of glaciers, for example, understand better what are the phenomena in the environment that affect the pollution in different areas of the Earth. So remote sensing through satellites is not new. What CubeSats are doing is basically to democratize that, to allow not just NASA or like the National Space Agencies to put sensors up there for your own specific application and have the data delivered directly to you instead of through many third parties that you cannot even trust, perhaps. Another interesting direction, which I think is definitely going to happen because I see many efforts going that way, is to put up there not just one CubeSat, but what's called a constellation of CubeSats. So a truly distributed system in space where the individual devices can coordinate and achieve in a distributed fashion something that perhaps would require one big, large satellite. But now you can achieve with tens of hundreds of small CubeSats that we perhaps can put up there, not just NASA.
And I find that really fascinating because you can start imagining like the version of Planet Lab with a constellation of CubeSats. It should be, and people can program them and run different kind of protocols. That would be really amazing. I guess the thing which I would like you to share a little bit about with the audience is, what is the process? Because this is like, you're creating the sensor, you're creating a CubeSat. How is that different from creating a normal sensor system? And second, what is the process of actually, what's the timeline for getting it all the way up into the space?
So it's okay. Keep in mind, right now there's not really a stable process for doing that. It all depends on the specific opportunities you have. So if you wanted, you could start developing a CubeSat from scratch get in touch with one of those private companies that organize periodic launches using their own launch rockets, and basically do everything internally. At some point, you would deliver your CubeSat as it is to these people, and they would load it on the rocket, and at some point you'll start receiving data magically. If you do things that way, you should be prepared to spend roughly, I would say, €500,000 for one CubeSat, everything included, turnkey solution. We didn't have €500,000, and we still don't have it for our own CubeSat research. So what we do is, and what I would actually suggest most people in the audience to do if they're interested in starting research in this area, is to piggyback your work on an existing CubeSat program. And there are many of them. For example, in our case, we have been establishing a nice collaboration with the Indian Space Agency. The work on Hummingbird, for example, was not carried by CubeSat per se. On that same CubeSat, there were like 4 or 5 other systems experimenting and researching totally different problems, and we only had one CubeSat basically. So you share the cost, but most importantly, you can pick the brain of the people you work with, and get up to speed much faster than compared to if you were alone doing this.
Building on that, one of the things which was asked was like, how do you actually get all this data? If you're taking a camera data, how do you get that? What kind of a link do you use? Are you using 60 gigahertz, millimeter wave? Are you using Wi-Fi? What kind of a link would work at that kind of a range to send something like a high definition video?
So we don't get the raw pictures. That's one thing. What you do in most of the cases is to locally process pictures and get down only the data you're really interested in. Because the RF capabilities are nowhere near what you would need to send down the raw pictures. In our case, but again, it all depends on the specific CubeSat and the infrastructure of the supporting company you rely on. In our own work, we have a very low bandwidth, long range proprietary protocol that we don't touch it. We have an API to the RF subsystem of the CubeSat, and there is a network of receivers on the Earth that eventually get our data on a storage server. In full honesty, we have no idea how it ends up there. We have the API on the CubeSat, and we know that if everything works, eventually we'll find the data on that storage server. So this is the drawback of this kind of things. I mean, it's really a totally virgin and uncharted territory. So there's not really a stable process. There's not really a stable architecture or anything. Something I'm involved in that I think it would be really important here is to define a common architecture for the CubeSat, at least to start with. So that, for example, like, let me get back to the Planet Lab analogy. If I want to test X and Y, I know that the APIs I have are these and these and that, and I know that the rest of the system looks like this. So I know exactly what I need to connect to what to do my own research. But in full honesty, we're kind of far from anything like that. It's really pretty much a ad hoc process right now.
So I'm going to switch gears a little bit and get in Tanzim. One of the questions which I think is on everyone's mind is, as grad students are listening to this, what kind of a future mobile health applications do you think are useful and worthy for the research community to work on? And I think with COVID-19, that's also the kind of the question, right? Is that a short-term question? Do you think that is that other interesting and impactful problems we can work on even for COVID-19?
Yeah, I think there is definitely a lot of interesting kind of problem. And I think it's a great time to kind of think about that, because with COVID-19, although it's terrible, but I think at least within the US, it will cause a shift in healthcare and get a lot of people to change how healthcare is reimbursed and all those things that have been a barrier so far in terms of really leveraging and taking advantage of a lot of technology solutions, right? We've seen even kind of Medicare, Medicaid making quick decisions, FDA approving things more quickly just because of the demand. So I think now is the perfect time. So with COVID-19 particularly, I think there is a lot of interesting work to be done in thinking about what do you need to measure beyond contact tracing, of course, right? So there are work that I'm doing, including Raja Lakshmi, your former student, right? In thinking about how can you track symptoms in a contactless way without burdening the user beyond the hospital, right? So, and the other thing is that even with hospital, like, there is no way with major hospitals that they get even pulse ox reading that can warn the physician. Most people don't buy a pulse ox, right? So how can you even think about new types of like commodity hardware-based sensing, and something that we've been working on. So, and beyond that, I think there is the aspect of health as an ecosystem, right? So when we often think about the patient and the doctor, but as soon as you leave the doctor's office, it's not just the patient and the doctor, it's their caregiver, and caregiver can come in very, very, very different form, right? For children, it's their parents. For elders, it could be a family member. There would be people who suffer chronic illness or recovering from a kind of surgery. There's a long-term aspect of it. And I think how do we kind of bring in the expertise of the doctor in the moment and actuate and measure, right? So I think there is a lot of opportunities of AR, VR in terms of if you have to inject something every day, are you doing it right? If you have to do blood draws, can you do it right? And how can you actually guide someone who doesn't need to be an expert phlebotomist to actually intervene on themselves? So it's not where you would put very expensive robotics there, right? So I think there is this whole kind of notion when we talk about kind of immersive care is you need to think about going just the telemedicine where it's video conversation to actually making it interaction in the doctor's office where you're measuring things, you're looking at responsiveness and reacting, and actually enabling the patient or the person with them to actuate on the users in an accurate way. So I think there's a lot of problems there in terms of how do you get a task done where you're doing labs on the users in their home, and also bringing in it's a partnership between kind of the caregiver as well as the patient. So in one example, one of my colleagues who work on it is with home health aides, right? And that's been a very interesting kind of dynamics because they're also a risk factor. Home health aides are actually treating the vulnerable. They're going between different houses. In New York City, they were taking the public transport. So understanding how we can measure and use these human resources in a safe manner is also another interesting aspect of where embedded tracking can be very helpful.
So I really appreciate what you just said, which is basically with COVID-19, one of the, if only any positive things has been that the healthcare system has been very, very pushing back any kind of a mobile health applications for the last 2 decades. But with COVID-19, they've been forced to really adopt. So it kind of feels like the gold rush of mobile health, where lots of the changes are happening and finally mobile technology is getting adopted. There's a lot of remote monitoring, the bandwidth requirement, everything is basically actually transforming in the healthcare system. So I think it is actually, if grad students are looking for impact, this is the time to work on mobile health or embedded systems for health, because you can actually potentially get your system to change the lives of multiple people. So one question which I wanted to bring both of your input towards is, it seems like in both the kind of projects you guys do, it's very interdisciplinary in nature. You do things which are systems, networking, embedded systems, health in the case of Tanzim, and in the case of Luca, you're interfacing with people who are building satellites and shooting rockets. So how do you get students excited? And these are longer term than just writing a paper, having an idea and simulating things. It's much longer term because you need to basically implement all these things and learn. You don't have one just bag of tricks you can just keep hammering to multiple things. It's more of like you need to learn multiple domains and build real systems which can be deployed. What is your advice, and how do you navigate this whole path for grad students and yourself? You can probably start with Tanzim, and then we can go to Luca.
Okay. So I think that's something that I had to deal with kind of throughout my career. Is like, who am I? And I think I still that's a valid question for me. And I think one of the things that really I would say is, if you think about the impact in, like, what does impact mean for an individual, right? So it can be there are kind of paths to having paper in top tier venues, but I think if one of the things that as faculty and as institution, I think we should kind of push also is that as computer science and all the work that we do grows, it is interfacing with society, and ultimately we would have lasting impact by taking on larger problems, but also making it clear that there are really interesting technical content there. So I think it's from a faculty's point of view, I think it is important for all of us to highlight where the technical problem is, where there are risks, and kind of thinking about mitigating risk. So I think one thing that was very helpful for me is choosing a community that is accepting of the work that we do, and as willing to kind of grow. So, and for me, it's been kind of straddling between communities as well to a certain extent. So I've been involved in kind of Mobisys, Census community as well, quite a lot. I would say my home community has been UBCOM, and really choose the right community. And it's okay to sometimes straddle between the communities to give the right exposure for the work where it will get adopted. And then of course, then there is the cross-disciplinary venues of clinical kind of venues where maybe that is something where you try to do kind of your most impactful clinical work. So having that balance, I think, is important. And the other is to also highlight, I think, in a lot of the cases who have been done a lot of kind of interdisciplinary work, students have gone on to really interesting jobs and even academic positions. So that can be a motivation of how people have achieved success in different ways, and highlighting those. But at the same time, there is probably more. It requires more openness to risk taking.
I think we are actually running out of time. So I would like to thank both the panelists, Luca and Tanzim. Thanks a lot. There are a couple of outstanding questions on the Slack, so if you can answer. So the next session is on wireless, and Aaron is going to be leading it. Thank you so much.
Thank you. Bye.
Bye.